In this video, we introduced a new multi-rotor based payload transportation solution which can carry the payload by simply putting it on the top of the platform. Conventional multi-rotors have several issues with transporting the payload. First, some payloads such as liquid are vulnerable to undesired motion, and especially, conventional drones cannot maintain constant fuselage attitude during the flight. And second, the payload with excessive size cannot be transported even if the mass is light, because most drone carries the payload underneath the fuselage, and it can hinder the aerodynamic behavior of the propeller-based propulsion system. To overcome the issues, we designed a new type of platform. The proposed platform has a cubic exterior, and all propulsion systems are housed inside the fuselage. Then we can place the payload above the fuselage, therefore a payload size limitation can be relieved. The propulsion system is also newly designed. At the core of the fuselage, the servo mechanism is placed with two arms attached to each axis, axis 1 and axis 2, where a pair of propeller thrusters are installed on the edge of each component. Then, by controlling the servo angles theta 1 and theta 2, we can distribute thrust on each axis vertically and horizontally. Utilizing the novel propulsion mechanism, we can make the system maintain zero roll and pitch attitude during the translational motion. The video and the graph show that the attitude of the fuselage remains zero while the platform moves in a rectangular course. However, if we load the random payload on the top of the platform, then the physical property of the entire system changes. Especially, the center of mass position may change severely, which generates undesired torque during the translational motion and brings undesired attitudinal motion that hinders the stable attitude control performance. To overcome this issue, the actual center of mass position must be identified, so we developed a new model-free center of mass position estimation algorithm. To validate the performance of the proposed algorithm, the experiment was conducted. First, we placed the 200-gram weight on a specific position. Then, we apply a sinusoidal dither signal to observe undesired attitudinal motion. Then we capture the undesired motion from the sensor data and process it to estimate the center of mass position. The video shows that the center of mass position is estimated correctly. The flight experiment with an actual unknown payload is conducted. We placed an unknown payload in a random position and started to estimate the center of mass position. Then, we compare the flight performance with and without estimation, where the flight after estimation shows improved flight performance on carrying the payload more stable. A secondary experiment with a longer travel distance was also performed, and the proposed algorithm showed better performance.